Welcome to week 6. In this week, we are going to discuss about trees, binary trees, BSTs, and the amortized analysis. So let's start with the tree. So a tree is a hierarchical data structure. It's a nonlinear data structure and it's a hierarchical data structure in which we organize the data in a tree format. Always remember that a tree does not have any cycle, right? It is, so we call it as a connected acyclic graph. A cyclic graph which does not have any cycle. A cycle is when you start from one point and you can reach up to the same point again. That is called as a cycle. If you start at a point and you reach back to the same point. It does not have any cycle. That means there exists only one path between every pair of nodes, and it is a tree is called as a minimally connected. Minimally connected means if you delete any of the edge from the tree, it will become disconnected. If you delete any of the edge, like for example, if your tree is something like this, and you delete this edge, so it will become disconnected, right? So there are lots of applications of trees, in real world and like organizational chart where you are having a CEO, then some managers working under him, then some employees working under him, or you have a family tree or the file system directories. There are plenty of applications of trees to which we can match our tree. If you see over here, these are the this is a structure of a tree. Like tree is here A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Right? So the root node, the top node is called as a root node. The top node is called as a root node. Right? The top node is called as a root node. Then we have, these are the edges. Like if you can see, this one is edge, this one is edge, these are the edges. The value in a node, is called as a key. Like A, the root node has the key of A, then the child of root node, which are B and C. The keys are B and C here. Then the child of B are D and E. A tree is always made up of several subtrees. Like if you can see over here in this triangle, these B, C, B, D, E, it is a subtree. In the same way, this CGF is also a subtree. This CGFOP, this portion, this is also a subtree. In a tree, and if we talk about a normal tree, in a tree can have any number of child. A tree can have any number of child, 0, 1, 2, 3, any number of child, right? Now, the, the child who share the parent, are called as the sibling. Like D and E are the sibling, G and F are the sibling, O and P are the sibling, K, L, M are the sibling, but H, I, J are not sibling because they are not sharing their parent. The the nodes which do not have any child, are called as leaf nodes. Like for example, you can see this K, L, M, N, O, P, G. They do not have any child, so these are the leaf node. The nodes which have child are called as non-leaf node. These are also, the leaf node are also called as external nodes, whereas the non-leaf nodes are also called as internal nodes. So the topmost root, which is the node A, has no parent, that is the root node. A is the parent of B and C. B and C are the children of A. Siblings, nodes with the same parent, are the siblings. Leaf or external nodes, a node with no children is called as a leaf node. A node with at least one child is called as a internal node or non-leaf node. And the edge, the link from parent to child, is called as a edge. Now, there are some more terminologies like a path, a sequence of nodes connected by edges. Like for example, if I'll say the path from node A to node K, the path from node A to node K, it will be, let me change the color, it will be from A to B, B to D, D to H, and H to K. So this is the path, A to B, B to D, D to H, and H to K. So this is the sequence of edges. And make sure in a tree there is a unique path. There is a unique path between every pair of nodes. You cannot reach from node A to node K via any other path. Ancestors and descendants. A is the ancestor. Look here. A is the ancestor of node G and G is the descendant of node A. Like we have in the family, right? Depth, the depth of a node. Just one more thing. This is the total height of the tree, that is 1, 2, 3, 4, 5, and there are different levels of each node. Like at level 0, A is at level 0, the root node is always at level 0. Then B and C are at level 1, D, E, G, F are at level 2, H, I, J are at level 3, and K, L, M, and O, P are at level 4. Now, a node's depth is the number of edges back up to the root, and the depth of root is 0. And the node height is the number of edges to its most distant leaf node, and height of a leaf node is always 0. So height of the leaf node is always 0, and height of the tree, the height of the root node, that is called as the height of the tree. And the degree of a node is the number of children a node has. Look, for example here, the node A, its depth is 0, but height is 3. Why height is 3? The longest path from A to B to a leaf node. The longest path to a leaf node. So A to B, B to E, E to H. Longest path. Or if you go from A to C, C to G, G to I. These are the two longest paths. So the sequence, the number of edges are 3. So the height of node A is 3. In the same way, the height of node C, is 2. Because if you check its leaf node, longest leaf node, from C to G, G to I, 2. There are two sequences, so the height is 2. The height of the height of node G is 1 and the height of node H and I is 0. But depth is 3. Make sure the height is always counted from downward to upward, whereas the depth is counted from top to bottom. So these two are the depth G. If you see, the node G is at depth 2 and height 1. Because if you count it from C at its bottom, there is one path, one sequence of path from to node I, from G to I. So the height is 1, but towards its root node. If you go to its root node, there is a path of length 2. So its height becomes 2. So in case of depth, you are going to check the length up to the root node. And in case of depth, you are going to check the length up to the root node, and in case of height, you are going to check the length up to the leaf node, right? Okay. Then we move on to the binary tree. If in a tree, each node can have at most two children, either 0, 1 or 2. Then it is called as a binary tree. Since it can have at most two children, we call it as a left child and right child. So 2 is the left child, 3 is the right child of node 1. 4 is the left child of 2, 5 is the left child of 2. Now there are several types of binary trees like full binary tree, complete binary tree and perfect binary tree. Full binary tree where every node has either two children or 0. That means it cannot have one, either 0 or 2. Complete binary tree where every level is completely filled except the last one, as we have discussed in the heaps also, right? And perfect binary tree where all internal nodes have exactly two children and all leaves or leaf nodes are at the same level. If you see here, the complete binary tree. This is a complete binary tree. Each node has exactly two childs and each level is completely filled except the last one because this level is not completely filled. Full binary tree where each node can have either 0 or 2 children. But if you remove these two, the 6 and 7, then still it is a full binary tree. A perfect binary tree where each node has exactly two childs except the last level, except the leaf nodes, and the last level is also completely filled. Then we talk about the tree traversals. That how we can traverse a tree, how we can read the values in a tree. So there are few traversal types. One is the in order, one is pre-order, and one is post order. In order, okay, before that I'll go with the actually binary search tree. So a binary search tree is that satisfies a ordering property. And what is the ordering property is that the value of left node should be less than the value of its parent and the value of parent should be less than the value of the right node. Value of left node should be less than the value of parent and the value of parent should be less than the value of right node. For example, if I do it 10, here is 2, here is 12. So 10 is the parent, 2 is the left child, 12 is the right child. So the value of 2 is less than the parent node and the value of parent node is less than the value of right node, which is 12. Now if I further write it like this, like 6 and 15, it should be, this condition should be true for all the subtrees, for every parent child in the tree. So 6 is less than 12 and 15 is greater than 12. So it is a BST, that is binary search tree. And yes, duplicate values are not allowed in a binary search tree because we cannot apply the condition of less than or greater than for equal values. So equal values are not allowed. For example, if you see here, this is a complete so binary search tree like 25, 30, 35, 40, 45, 50, 60. Now, if you go on the traversal of these one, if you traverse a in order, if you traverse a in order, so if you traverse the left node first, then root node, then right node, it is called as in order traversal. If pre-order, root node first, then left node, then right node, so it is the pre-order. And post order is left node, right node, and root node. This is the sequence follows. So in order, the root goes in the middle In pre-order, root goes in the first position, and in the post-order, node goes at the end position. Now, whenever you traverse a binary search tree and it is a in-order traversal, you will get all the values in ascending sorted order. Like for example, this is a tree, this is not a binary search tree. These are the keys 1, 2, 3, 4, 5, 6, 7. If we perform its in-order traversal, so in-order traversal is left node, then parent node, and then right node. So left, parent, right. So left node, you start with the root node, which is 1. So left node is, the left node of 1 is 2. And the left node of 2 is 4. So the left node, so 4. Then parent, so the parent of 4 is 2. And then right node, so it is 5. So 4 to 5. So this subtree is completed. Then you will go for the again. So this left is completed. Left is completed of 1. Then you will go for the parent node, which is 1. So 1 will be traversed. Then you go towards the right side. So right side is also left, parent, right. So left node 6, parent node 3, right node 7. So its in order traversal becomes 4 to 5, 1, 6, 3, 7. In the same way, the traversal for pre-order. For pre-order, it is root left or the parent left right. Parent left right. So if the parent is 1, so the 1 will go first, then left node, which is 2. But it is itself a parent of 4 and 5. So again, parent left right. So parent left right. So 2, 4, 5. Then we go towards the right side because parent is completed, its left is completed, then we go towards the right side. In the right side again, parent left right. So parent left right, which is 3, 6, 7. 3, 6, 7. In the post order traversal, we say it left, right, parent. Parent goes at the end. So left 4, right 5, parent 2, then left 6, 7, 3, and then parent 1. We do one more type of traversal, which is label order. In case of label order traversal, we read all the elements label wise, like element 1, then 2 and 3 at the second level, then 4, 5, 6, 7 at the third level, and so on. Sorry, at level 0, 1, and 2. Right? So the label order traversal will be 1, 2, 3, 4, 5, 6, 7. So if we summarize the binary tree, the tree models are hierarchical data. Binary tree, in case of binary tree, each node can have at most 2 children. Traversals are in order, pre-order, post-order. In case of binary search tree, we enforce the ordering property. Height determines the performance. For base case, the height of the tree is big O of n log n, and for the worst case, the height of the tree is big O of n. Then, let's move on to the next topic, which is the amortized analysis. In week 1, we study about the complexity of an algorithm. That what is the best case, worst case, and average case complexity of an operation. Amortized analysis is a technique basically for determining the average time per operation in the worst case. Like if you are having a sequence of operations, not exactly one operation, if you are having a sequence of operations, then what is the overall performance? Average time per operation in the worst case scenario. That is called as the amortized analysis. It is not a probabilistic technique. You are not finding the probability here basically, but it's an average case analysis, right? Unlike the average case analysis. It provides a guaranteed worst case average. We get an exact formulation here. It is a way to understand the true cost of an operation that may occasionally be expensive. For example, there are a number of data structures which are very cheap almost all the time, but the few operations are very expensive. So the amortized cost is the overall cost, including the many cheap operations and one expensive operation. Right? Just for example, the cost of an expensive rare event like a car repair is amortized over the many days of cheap driving. Right? Okay. So the definitions which we use in case of amortized analysis, one, we calculate the actual cost. Actual cost is the true cost, immediate cost of the ith operation. Amortized cost is the assigned cost we use for the analysis. It may be higher or lower than the actual cost. So the total amortized cost becomes the sum of all amortized cost across all the n operations, like amortized cost 1 plus amortized cost 2 up to the n. So total actual cost is sum of actual cost across all operations, like cost 1, cost 2, cost n. And the fundamental operation equation which we use, that the total amortized cost must always be greater than or equal to the total actual cost. Total amortized cost should always be greater than equal to the total actual cost. For example, if we are having an array and we are doubling its size at runtime. So, if an array fills, we double its size, copy all the elements, and then we take it, right? So, suppose we have an array that starts with capacity 1. Every time the array is full, we double its size. So, what are the operations here? Insert elements one by one into the array. So if we calculate the actual cost, insert one element, cost is 1, insert second element. So the cost will be 2. Why the cost will be 2? Because you are allocating a new array of double size, and then first you will copy the previous element, which is the first element, and then you will insert this second element. Now, if you insert the third element, then again the cost will be 3. Why? You allocate a new array, the size will be 4. Because in second step, the size was 2 and we are doubling the size, so size will be 4. So your size is 4, then you copy two elements and then insert. So you are copying the element 1 and 2 and then you insert element 3. So the cost is 3. Then if you insert fourth element, the cost is 1. Why cost 1? Because no resizing is required here. You are just inserting the element. And then insert fifth element, the cost is 5 and so on. So the actual cost varies a lot, sometimes 1, sometimes much larger. So what will be the amortized cost? Instead of tracking the messy actual cost, we spread the expensive operations evenly. If we assign 3 units of amortized cost per insert, then most inserts, the cost 1, are overcharged, leaving the credit behind. So rare expensive operations like copying 4 or 8 elements can be paid using that saved credits. So if we check by using the fundamental equation which we just did, for 8 insertions, the total cost is 15, but the total amortized cost using 3 per operations, it is 24. So the inequality holds, which is 24 is greater than equals to 15. So thus, although the actual cost spikes, the amortized cost gives a smooth bigger of 1 average cost per insert. Now, there are 3 methods of amortized analysis: the aggregate method, the accounting method, and the potential method. In case of aggregate method, we find the total cost for n operations and then the amortized cost is per operation, so Tn divided by n, right? So it is, you need to find a closed form for Tn. In case of accounting method, we use the banker's method. So the idea here is you assign different amortized costs to different operations, overcharge cheap operations to store the credit that pays for future expensive ones. So it's something like you are thinking that you are prepaying for future cost. And the potential method, that is the physicist method, it defines a potential function phi on the state of the data structure. The amortized cost is the actual cost plus the change in the potential. So amortized cost is the actual cost plus potential after operation minus potential before operation. For example, again let's see the same example. Insert n elements into a dynamic array by doubling. So let's again take the example of inserting the elements into a dynamic array, and whenever the capacity is full, we need to double it, right? So if we use the aggregate method, total cost is sum of all insertions. So most inserts cost just one, just placing the item. Occasionally when we resize it, then we pay extra to copy the existing elements. So for n insertions, every element gets copied at most once when the array doubles. So the total copy cost is less than equals to n. Total insertions is n. So the total cost becomes less than equals to 1. So amortized cost per insert will become Tn divided by n, which is n equals to 2. So which is 2n over n, which is 2, and 2 is a constant number, so it becomes big O of 1. So it is the simple average for all the operations. The aggregate method takes the average of all the operations. Accounting method, which is the banker's method, let's assign an amortized cost of 3 to each insert. One coin pays for the actual insert and 2 extra coins are saved for future copies. So first few inserts. If you insert 1, the actual cost is 1, so amortized is 3, so you are saving 2 coins here. Then you insert one more, number 2, actual cost is 2, which is insert plus copy, so amortized cost is 3. So you pay 1 coin, use 2 saved coin to cover the copy. Then you insert 3, so actual cost is 3, which is insert plus 2 copies, right? So amortized is 3, so we can use the saved coins again. This way, the credit always cover the full expensive operations. Again, the amortized cost per insert is 3, which is big O of 1. So the idea is you are overpaying for the cheap operations to fund, so that the later on you can use the saved credits for the expensive operations. Then the next one is the potential method, which is also called as the physicist method, in which we define the variable phi, which is capacity minus size. So it measures basically unused slots in the array. Amortized cost here is actual cost plus change in potential. Change in potential means after operation minus before operation. Potential after operation minus potential before operation. For example, its array doubles from size 4 to 8. So actual cost will be 5 because you are inserting one element plus you are copying for existing element. So the cost becomes 5. Potential before 0 because array was full, and potential after becomes 3 because 3 slots are still empty. For those 3 slots, you just need to perform one operation. So change in potential is 3. So amortized cost becomes 5 plus 3, which is 8. So for normal inserts, actual cost is 1, potential decreases by 1, and so amortized cost is 1 plus negative 1, which is 0. And over many inserts, if you perform so many insertion operations, the amortized cost averages to big O of 1. So we say that potential stores the energy of unused space, which pays for the future copies. So there are 3 methods to find out the amortized analysis. One is the aggregate method, average the total work. Another one is accounting method, overcharge for cheap inserts and save credits. And one is the potential method, in which you use a potential function, which is capacity minus size. All 3 methods shows that inserting into a dynamic array takes constant amortized time. If we perform the comparison of all of these analysis methods, aggregate method, the core idea is to compute the total cost for all the operation and divide by the n. Whereas in accounting method, overcharge cheap operation, save the credit for the expensive ones. And in the potential method, define a potential function which is amortized equals to actual plus phi, difference in potential. How does aggregate function works? It show that each element is copied at most once when array doubles. So the total cost is less than equals to 2n. So total cost is, amortized cost is 2n over n, which comes out to be big O of 1. In case of accounting method, assign an amortized cost to each operation so that the extra saved coins can be used later on for the future operations. Each operation pays ahead, keeping inserts at big O of 1. And the potential method, physicist method, it define a function phi, which is capacity minus size. So it is for the unused slots. You are defining the potential for unused slots. So amortized cost smooths out to big O of 1 across all inserts. So aggregate, average all cost, accounting prepay with credits, and potential store energy in data structure state. So for all of these three methods, by using all of these three methods, the big O of 1 amortized insert into one dynamic array. So that's all for the week 6. Let's meet with you in week 7 with your projects. Thank you. Bye. Take care.